So today we're going to learn about tissue engineering. So in the medical profession, there are many instances where the body cannot heal itself in a healthy way. Certain injuries cannot be healed with conventional medicine. This is why people in the medical profession have turned to tissue engineering to heal these injuries. There are many forms of these engineered tissues, like induced stem cell grafts or artificial tissues. Artificial tissues exist by the creation of smart materials. Smart materials are an artificial replacement for human tissue that through new technologies are not rejected through the immune system. So basically what that means is that we can have these artificial replacements like metal objects, or maybe even little strings and things that hold you together. But what's special about them is they won't be rejected by the immune system. Because the main problem with objects like the pacemaker is if you just put them into the body, your immune system will attack them, they'll reject them, and eventually they'll move them through the waste. Okay, smart materials are anything that are made artificially bioengineered objects, like a pacemaker or contact. These materials are man-made tissues. They're made for medical purposes. There are also medications that can help you help recognize that these are to help, not to harm. There are also, these medications are mostly used in transplanting tissues, like replacing a human heart valve with a pig's heart valve. For the use of smart materials, the body would often reject transplanted tissue once it recognized it as foreign. The application of smart materials was a major step in creating artificial tissues.
So how do they create it so that the body doesn't reject it?
Well, there's many different ways, but one of the most common is they actually put an enzyme coating around the object. Like this is what they use in the pacemakers. So basically they just create these little enzyme things. And as you guys know, in the human body, how an antibody tells if an object is foreign is it binds to protein sites. So what this does is this enzyme coating just has a whole bunch of protein sites on it, so it will not recognize it as a foreign object. Does that make sense?
Yeah, it does.
Yes.
So then essentially, could you put anything in the body of the enzyme coating and the body wouldn't reject it, like a penny?
Technically, well, yeah, you can. Chris?
How about a Hot Wheels car?
I guess you could. Alright, so current research. In terms of tissue engineering, smart materials have helped pave the way for future advances. Artificial tissue engineering would not be possible without this. We need tissue engineering because some tissues can be badly damaged beyond natural repair. To fix or replace these tissues, we create new ones. Other than artificial tissues, there are other possible routes for tissue engineering, like induced pluripotent stem cell grafts. I'll explain those later. And embryonic stem cells. One of the most common uses of induced pluripotent stem cells in tissue engineering is creating skin grafts for those people who have severe burns or skin diseases. Alright, so as you can see in this picture is actually an induced pluripotent stem cell. And I'll explain how we induce pluripotency soon. Okay, so it takes about 3 weeks to grow enough cells to create a skin culture. And actually we're going to have a little demonstration later in the lesson. Okay, doctors take a patient's own cells, a fibroblast cell. They are found in the bone marrow. Okay, so we do this by injecting a retroviral technology to mutate 4 distinct genes in a human fibroblast. Those 4 genes differentiate the cell. So what that does is without those 4 genes, this cell can basically be any cell you want it to be. So again, you inject a different retroviral system and it changes it to the cell that you want it to be. Okay, so this was the first real application of induced pluripotent stem cell tissue engineering. Okay, since the discovery of the engineered tissue graft, there has been many applications of the new technology. There have been successful tissue cells of multiple different types. Doctors have been successful in creating heart cultures. In Tokyo, in 2002, a 12-year-old boy had a heart defect in the left ventricle. His doctors were cleared by the hospital and his parents to perform the first tissue engineering cardiac graft. Doctors removed some of the peripheral vein about 2 centimeters and harvested it. After a few weeks, they performed the surgery, removing the defective tissue, replacing it with engineered tissue. Alright, so this is actually a picture of the surgery. So as you can see, this right here is the heart. And if you look really closely, you can see little lines. So this whole area right here was the engineered tissue. And it was successful. The boy actually lived a normal life after this. It was actually the first artificial heart transplant that was used the iPSC cells. That's induced pluripotent stem cells. Alright, but there is major problems with this technology because if you have the genetic defects, they will not be able to perform the surgery. Because if they take your cells with the same genetic defects, they'll just grow the same defects. Make sense? Alright, any questions?
So then you take cells from another person that wouldn't have that genetic defect?
Yes, and then you would use that medication that I talked about earlier so the heart would not be rejected.
Okay.
Okay? Cool. Yes?
What happens to the tissue once it's rejected? Do they just leave it inside?
Well, yeah, actually the body will take care of that. The immune system will attack it once it finds it foreign, and it will then turn into waste. Go through your bloodstream and cause it.
But if that foreign tissue is like a transplant part of your heart, wouldn't you just die?
When it's rejected, yes. That's why we had to invent smart materials.
Okay.
Alright?
Yeah.
Cool. There are actually multiple problems with tissue engineering. Tissue engineering is focused on research that will help cure previously incurable medical conditions. Research is centered right now on constructing cardiac tissue, cartilage, and making neuron grafts. Creating successful neuron grafts will create possible cures for conditions as lack of sensation to paralysis. The basic concept is the same as a skin graft. To create a culture of a neuron cell is the same thing. It's created like the same size, the same shape. What they do is they create a culture, and then they take away the excess cells, place it in the affected area. Doctors then will add an adhesive tissue around the edges of the culture and place it where it belongs. But there is one major problem with this. I mean, skin cells, they can survive outside the body, right? But neuron cells can't. So one of these problems was fixed by creating these extracellular matrix. It says right there. And what those basically do is, it's similar to an incubator for everything else. It simulates the human body. It has the right nutrients, it has the right parameters for cell life. Alright? Okay. Another problem is creating enough cells. Because even with this extracellular matrix, there is a growth problem. I mean, you can't make gigantic extracellular matrix because there's just not enough nutrition. Okay, cut that. That was one of the main problems is that unlike skin cells, neuron cells cannot survive long outside the body. To solve this problem, scientists are using extracellular matrix that are substitutes for cells. In these matrices, they can actually thrive and survive. It's basically simulation of the human body. Okay, this is a cell and an extracellular matrix, obviously. This is magnified. All this area is the cell, all this is extracellular matrix. As you can see, there's little pockets all along here is needed nutrients. Alright, okay. Another problem with current research is creating enough cells to do the graft. The culture can grow successfully and they bind together, but to create enough neurons to replace a broken spinal cord, you need a significant number of cells. There have been many successes with the neuron cells being grafted in small amounts. And also the cells have been morphed into the same phenotype as the hosts, making them indistinguishable from surrounding tissue, and they are fully functional. Resources in tissue engineering. To create these organs, scientists are using many different materials. Currently, scientists have been using animal organs, smart materials, and induced pluripotent stem cell grafts, and sometimes even embryonic stem cells to advance tissue engineering. Induced pluripotent stem cells are taking adult stem cells, which are induced into pluripotency. Pluripotent stem cells are cells that are able to change into any type of cell in the human body. So that is basically, like we did before, is like I talked about before, is taking a fibroblast and you inject the little thing into it, and then you can program it to be any cell you need. Maybe an eye cell, hair cell, hand cell even. I mean, potentially we could create body parts.
Is there some cells that are more difficult to create than other ones? Like, say,
theoretically, no. But real world application, some are harder to grow.
Okay.
Like it is harder to grow neuron cells than skin cells.
You said there's like something about the small, like they've only done small amounts.
Yes.
Why is that only small amounts, not large amounts, like successful?
Right now, what's happening is the cultures and the extracellular matrix, they haven't perfected technology, so they can't create larger amounts. They just don't have enough resources. Because if you have a large amount of cells, they deplete resources faster, right?
Yeah.
So they just run out of the resources faster, and they just cannot survive as long.
So they don't have enough to upkeep a large amount of those.
Yes.
Okay.
So that's why right now scientists are really trying to improve extracellular matrices so they can have cells survive longer.
Okay.
Okay. That's pretty good.
Is that everything?
Yeah. Okay. So resources in tissue engineering. To create these organs, scientists have been using many different materials as we've gone over. Currently, scientists have been using organs, smart materials, induced pluripotent stem cells, and embryonic stem cells. Induced pluripotent stem cells are taking adult cells and inducing them, as we talked about before. Embryonic stem cells are also a promising direction in tissue engineering. Embryonic stem cells are already pluripotent, so we don't need to induce them. But that's another problem, is harvesting the cells and obtaining the cells. The problem is that with embryonic stem cells are not in your body. Therefore, they have to be harvested from an embryo. And it just creates another problem, because as we stated before, they might be rejected from the body. They're not recognized as our own tissue. So, they might be rejected. So, therefore, we use medications. Alright, the cell also has different genetic predisposition, which may cause serious health problems in the future. So if a person, let's say, you're getting a heart transplant, and we do not know this, that the person who got the embryonic stem cells from, they were going to have a heart problem, a heart defect. So if we create a new heart, that creates a new heart defect with engineered tissue. Animal parts have also been very successful in tissue transplantation. Normally they're using complicated sutures like cardiac valves that are hard to repair. Okay. So right here is a picture of artificial tissue. This is actually